is why you can't just fly straight to Mars. Mars looks close, at least close by space standards. We can see it from Earth. We know where it is. We have rockets powerful enough to leave our planet. So why can't we simply point a spacecraft toward Mars, turn on the engines and fly straight there? Because the moment you leave Earth, Mars is not waiting for you. Mars is moving. Earth is moving. Your spacecraft is moving. And all three are traveling through the gravitational field of the sun. Getting to Mars is not really about flying toward a planet. It is about predicting where that planet will be months in the future and arranging for your spacecraft to arrive at exactly the same place at exactly the same time. And that is only the first problem. Imagine standing beside a highway while a car passes you at high speed. If you wanted to jump into that car, you would not aim for where the car is right now. You would have to predict where it will be when you reach the road. Mars works the same way, except the road is hundreds of millions of kilometers wide, and both you and the target are moving around the sun. Earth travels around the sun at roughly 30 kilometers every second. Mars moves more slowly because it orbits farther away. So when a rocket leaves Earth, it does not begin from zero. It already has Earth's enormous sideways speed around the sun. That means the spacecraft is already in an orbit before its engines even begin changing its path. To reach Mars, engineers need to reshape that orbit, not simply point the nose of the rocket at the red dot in the sky. One common approach is to launch when Earth and Mars are positioned so the spacecraft can enter an orbit around the sun that intersects Mars months later. Think of changing lanes on a gigantic circular highway. You leave Earth's lane, travel along a new curved path, and if the calculations are correct, Mars reaches the intersection at the same moment you do. If the timing is wrong, there is nobody standing in space with a traffic sign telling Mars to wait. The planet keeps moving. You miss. So why not avoid all of this complicated orbital mathematics? Why not just keep the engines running and chase Mars directly? Now we reach problem number 2, fuel. Rockets consume enormous amounts of propellant. And here's the frustrating part. Fuel has weight. If you want to carry more fuel, your rocket becomes heavier. A heavier rocket requires more fuel to accelerate. But that additional fuel also has weight, so you need more fuel to carry the extra fuel, and then more fuel to carry that fuel. This is why rockets look enormous on the launch pad, while the useful spacecraft at the top is relatively small. Most of the vehicle exists to carry propellant that will be burned very early in the journey. So rockets usually do not operate like cars with the accelerator pressed for the entire trip. Their engines burn intensely during important parts of the mission. Then they shut down. The spacecraft coasts. For months. At that point, the spacecraft is not sitting still. It is falling around the sun along a carefully calculated orbit. That sounds slow, but the spacecraft may still be moving tens of thousands of kilometers per hour. And now we discover problem number 3. Arriving at Mars is not enough. You have to stop. Suppose you somehow flew a spacecraft all the way to Mars at enormous speed. Congratulations. Mars is directly ahead. Unfortunately, unless you slow down, you are not visiting Mars. You are crashing into it. On Earth, stopping is easy. A car uses brakes, a plane uses air resistance, control surfaces, spoilers, reverse thrust, and brakes after landing. In space, there is no road. There are no brake pads. To slow down with rocket engines, you have to fire them in the opposite direction. And that means carrying more fuel. The same fuel problem returns. So engineers use another tool, Mars itself. When a spacecraft reaches Mars, it can enter the atmosphere at enormous speed and use the atmosphere to help slow down. This sounds convenient, until you look at Mars's atmosphere. Mars has air, but compared with Earth, it is extremely thin. That gives engineers a terrible combination. There is enough atmosphere to generate dangerous heating during entry, but often not enough atmosphere to slow a heavy spacecraft safely by parachute alone. Imagine trying to stop a speeding truck using something barely thicker than a sheet. That is roughly the problem. A spacecraft enters the Martian atmosphere at tremendous speed. The air in front of it compresses and heats. The protective heat shield becomes extremely hot. The vehicle slows, but not enough. So engineers may deploy a huge parachute. That slows the craft further. Still not enough. Then rockets may fire. For some missions, the descent system has had to perform an entire sequence automatically. Atmospheric entry, heat shielding, parachute deployment, separation, powered descent, final landing, all in only a few minutes. And people on Earth cannot simply grab a joystick and correct everything in real time. Which brings us to problem number 4. Mars is too far away for instant communication. Radio signals travel at the speed of light. That sounds unbeatable, but space is enormous. Depending on where Earth and Mars are in their orbits, a radio message can take several minutes to more than 20 minutes to travel one way. So imagine watching a spacecraft descend toward Mars. You see something go wrong. You press a button. By the time your command reaches Mars, the spacecraft may already have been sitting safely on the ground or lying in pieces. This means a Mars spacecraft has to think for itself. Its computers have to monitor speed, altitude, orientation, terrain, engine performance, navigation, and unexpected problems. By the time Earth learns what happened, the spacecraft has already made the decision. Now suppose we solve that too. The spacecraft lands successfully. We have reached Mars. Mission accomplished. Not quite, because Mars immediately introduces problem number 5, radiation. Earth protects us in ways we barely notice. Our atmosphere absorbs and blocks a great deal of harmful radiation. Earth's magnetic field also helps deflect charged particles arriving from space and the sun. Mars does not provide the same level of protection. Its atmosphere is thin, and it does not have a global magnetic field like Earth's. That means astronauts on the surface would receive far more radiation than people normally experience on Earth. This is not something you solve with a thicker winter coat. Habitats would need shielding. One possible solution is to place living spaces underground. Another is to cover habitats with Martian soil. Water can also help provide radiation shielding. Engineers may eventually use combinations of local material, water storage, and specially designed walls to reduce exposure. But radiation does not only threaten humans, it threatens electronics too. High-energy particles can strike computer components and corrupt data. A tiny electrical disturbance inside a processor can flip a digital bit. A 0 becomes a 1. A command changes, a computer crashes. So spacecraft use hardened electronics, redundancy, error correction, and backup systems. Then comes problem number 6, dust. Mars is covered in it, and Martian dust is not simply the soft dirt you find in your backyard. It can be extremely fine. It can cling to equipment, it can coat surfaces, it can interfere with mechanical parts, it can reduce the performance of solar panels, it can work its way into seals and moving components. Imagine building a machine that has to operate for years while somebody continuously throws fine abrasive powder at it. That is Mars, and if people live there, dust becomes a human problem too. You do not want astronauts carrying large amounts of Martian material into living areas every time they return from outside. Future habitats may need specialized airlocks designed to keep dust outside. Spacesuits may even remain attached to the exterior of a habitat, so astronauts climb into them from inside rather than dragging dirty suits through the living space. But even if we control the dust, Mars gives us problem number 7, cold. Mars is much farther from the sun than Earth. Its thin atmosphere does not retain heat the way ours does. Temperatures can drop extremely low, so a Mars base is not simply a house with thicker walls. It is a life support machine. It needs heating, insulation, pressure control, oxygen, water, food, waste processing, electrical power, communication, fire protection, backup systems. If one of those systems fails on Earth, you may call a repair company. On Mars, the nearest replacement part may be millions of kilometers away, which leads to one of the biggest questions of all. Why take everything from Earth? Water is heavy, food is heavy, fuel is heavy, building material is heavy. Launching mass from Earth is expensive and difficult, so a long-term Mars settlement would eventually need to use resources already available on Mars. Mars has water ice. If future systems can extract that water, it becomes incredibly valuable. People can drink it, it can support agriculture, it can potentially be separated into hydrogen and oxygen. Oxygen can support breathing. Hydrogen and oxygen can also be useful for rocket propellant. This changes the entire mission. Instead of carrying everything from Earth, Mars begins supplying some of what the explorers need. The Martian soil could also provide material for construction. Rather than transporting every wall, brick, and protective barrier from Earth, future robotic systems may process local material into structures. Imagine sending construction robots before the astronauts. They arrive first, prepare the site, build protective structures, extract water, test power systems, and create a functioning base before humans ever leave Earth. That sounds much more practical, but now we encounter another enormous problem: power. A Mars base needs electricity every hour of every day. Solar panels are one option, but dust can reduce their output. Night exists, seasonal changes exist, and large dust storms can dramatically reduce sunlight. So a serious settlement may need multiple power sources: solar energy, battery storage, possibly nuclear power. backup generators of some form. Again, the word that keeps appearing is redundancy. On Mars, one system is never enough. If a single failure can destroy the entire mission, the design is not ready. Now imagine we solve all of that. Astronauts survive the journey, they land, they build a habitat, they produce water, they generate power, they grow food. There is still one problem nobody gets to ignore: getting home. Launching from Mars is easier than launching from Earth because Mars has lower gravity, but it still requires a rocket. That rocket needs fuel, it needs engines, it needs life support, and it needs to leave Mars at the correct time. Remember the orbital problem from the beginning. It comes back. Earth is not waiting in one place. The planets continue moving around the sun. You cannot simply decide on Tuesday that you would like to return home Wednesday morning. Mission planners have to wait for favorable positions between Earth and Mars. That means astronauts could be committed to long stays. If something happens shortly after arrival, the solution may not be go home. Home may not be reachable for months, and this is why Mars exploration is so difficult. No single problem makes it impossible. That would almost be easier. Instead, Mars gives us hundreds of problems that interact with one another. Add more radiation shielding. The spacecraft becomes heavier. More weight requires more launch capability. Add more food, more mass. Add more fuel, more mass again. Spend longer in space. Astronauts receive more radiation. Travel faster. You need more energy. Build lighter. You may sacrifice protection. Every solution creates another engineering trade-off. So could we make the journey easier? Possibly. One major improvement would be better propulsion. Traditional chemical rockets provide enormous thrust, but they consume fuel rapidly. Other propulsion technologies may offer different advantages. Electric propulsion can operate efficiently for very long periods, although it generally produces much lower thrust. Nuclear-based propulsion concepts could potentially reduce travel time for human missions if developed and proven. Shorter trips would help with several problems at once: less time in deep space, less food required, less exposure to radiation, less time for equipment to fail. That is why propulsion matters so much. Reusable launch systems also change the equation. If major rocket components can be flown again rather than discarded after every mission, launches can become less expensive and potentially more frequent. More launches mean more cargo, more equipment, more redundancy, more opportunities to send supplies before crews arrive. But even with better rockets, Mars does not become easy, because the real challenge is not distance. It is building a chain of systems where every link has to work. Launch from Earth, navigate around the sun, survive months in space, protect against radiation, arrive at Mars, slow down, land safely, generate power, find water, produce oxygen, grow food, control dust, maintain the habitat, keep astronauts healthy, and eventually launch again and find Earth. Miss one critical step, and there may be nobody nearby to rescue you. So why go at all? Because every problem we solve changes what is possible. The first spacecraft showed that reaching Mars was possible. Orbiters mapped the planet. Landers tested the surface. Rovers learned how to survive for years. New spacecraft continue improving navigation, autonomy, power, and landing technology. Each mission removes a little uncertainty. Each failure teaches engineers what not to do. Each success moves the next mission one step farther. And that may be the most surprising part of the Mars story. You cannot simply fly straight to Mars. You cannot leave whenever you want. You cannot keep ordinary rocket engines running forever. You cannot land like an airplane. You cannot depend on instant commands from Earth. You cannot walk outside without protection. And you cannot assume everything you need will be shipped from home. Mars forces us to solve every problem differently. But difficult does not mean impossible. It means the route is more complicated than a straight line. The path to Mars is not one giant technological breakthrough. It is hundreds of smaller breakthroughs working together. Better engines, better robots, better radiation shielding, better life support, better power systems, better autonomous computers, better ways to use resources already waiting on another world. One day, a human may look through a window and see the surface of Mars outside. When that happens, they will not be there because someone finally built a rocket powerful enough to point at Mars and fly straight toward it. They will be there because generations of engineers learned how to solve every problem standing between two moving planets. And that is why getting to Mars is so much harder than it looks, but also why eventually we may actually do it.